Hello, I welcome you all to this another interesting screencast. The problem reads that the platform is rotating about the vertical axis such that at any instant its angular position is theta equal to 4t to the power 3 over 2 radians, where t is in seconds. A ball rolls outward along a radial groove so that its position is r is equal to 0.1 t to the power 3 meters, where t is in seconds. Determine the magnitudes of the velocity and the acceleration of the ball when t is equal to 1.5 seconds. So we are being asked to find the angular velocity and angular in fact the magnitudes, right? So it's a combination of velocity along the groove as well as along the change of direction. Okay, so even in this particular problem we are going to use the polar coordinates. So what we are going to do is let's show these coordinates. So we have along the groove, which is our arrow, okay, in this direction like so. So this is our arrow. This is our arrow, okay. This is our arrow, and we do have our unit vector there, which we are calling u arrow. This is arrow, and then perpendicular to that we have let's say this is perpendicular, we have our theta. So this is perpendicular, so these are the positive directions that we are showing. So this is theta, we have the unit vector there, u theta, like so, in that direction. All right, so let's write down now the equations. We are not doing any derivations. So we know that both r and theta are changing with respect to time, so we are going to have some changing, right? The ball is going to be at different positions, right, along r as well as along theta direction. So r is given as equal to, what is r? R is equal to I saw r somewhere is 0.1 t cubed, okay, right? And let's find the first derivative with respect to time. R dot, which is just the r dt, so this is just going to be equal to 0.3, okay, t to the power 2, okay. And let's go to r double dot, which is just equal to second derivative of r with respect to time. This is just going to be equal to 0.6 t. All right, let's go to theta. Theta also here is being expressed in terms of time, okay, or it's a function of time, so it's 4t to the power 3 over 2, which I can also rewrite as 4t to the power 1.5. And then theta dot, which is just the theta dt, this is equal to of course we multiply 1.5 by this, this becomes a 6, right? This becomes a 6t to the power 0.5, right? 1.5 by 4 is a 6. All right, and then theta double dot, which is just also equal to second derivative of theta with respect to time, and this is just going to be equal to 3t to the power minus half minus 0.5. All right, and then we know that our velocity is just equal to VR UR like so plus V theta U theta like so. Okay, where VR is just going to be equal to R dot, okay, R dot, and then this is equal to 0.3t squared. Okay, right. We've been told that we are supposed to calculate these values at t equal to 1.5 seconds. Right, therefore VR at 1.5 seconds is going to be equal to, let's plug in those values. This becomes a 0.3 times 1.5 squared. So this gives us a 0.675 meters per second. Meters, right? Meters, right? Right. So let's go to V theta. V theta is equal to R theta dot. All right, and our R is equal to, again, how to derive this, you can get back to the books. Our R is equal to 0.1 t cubed, and then by theta dot is equal to 6t to the power 0.5. Therefore, this becomes 0.6 t to the power 3.5, and then V theta at t equal to 1.5 gives us 0.6 by 1.5 to the power 3.5. So this just gives us a 2.48 meters per second. So we know that the magnitude, the two are perpendicular to each other. This gives us VR squared plus V theta squared. And we know that our VR, we just calculated it as 0.675, and our V theta, we calculated it as a 2.48. Therefore, our magnitude is just going to be equal to 0.675 squared plus 2.48 squared, square root of that. This gives us a 2.57 meters per second. Alright, so this is the magnitude of our velocity. Okay, so velocity for this ball at t equal to 1.5 seconds. Let's move on to the acceleration. Alright, so we have the acceleration here equal to expressed as a vector. This is equal to AR UR and then plus A theta u theta. Then to check, you get back to your textbook to check how these are derived. AR is equal to A double dot minus R theta double dot squared, and then A theta is equal to R double dot plus 2R dot theta dot. Okay, so AR, we have already the double dot is a 0.60, okay, minus R theta dot squared. So we have R, what is our R? Is a point, that's a 0.1 t cubed, and then we have theta dot, which is 60 to the power 0.5 squared, right? Then we have A theta R double dot. R is just 0.1 t cubed, and then double dot is a 3t to the power minus 5 plus a 2. R dot is 0.3 t squared, and then theta dot is 60.5. Okay. Therefore, at t equal to 1.5 seconds, AR at 1.5 seconds is equal to that's 0.6 by 1.5 minus 0.1 by 1.5 to the power 3 times times 6 times 1.5 to the power 0.5 and everything squared. Alright, so here we have a minus 17.325 units of meters per second squared. Then A theta at 1.5, plug it in there. We have 0.1 by 1.5 to the power 3, okay, times wow, I can multiply this directly, right? So I can just say 0.3 0.3 times 1.5 to the power 2.5, right? Okay, that's 0.3 by 1.5 to the power 2.5 plus 2 by 0.3, that is 0.6, right? So we have 0.6 by 6, that's 1.2. So we have a 1.2, okay, by 1.5 to the power 2.5. Alright, so I have a 4.13. Okay, let me 4.13, maybe I say 4. round off that one there, meters per second square. So I have 2 by 0.3 by 6 by 1.5 to the power 2.5 plus 0.3 by 1.5 to the power 2.5. Okay. How come I'm finding smaller number? Okay. 0.3 by 1.5 to the power 2.5. Okay, plus 2 by 0.3 by 6 by 1.5 to the power 2.5 at 10.74. Okay, I think I made a mistake here. So this one is a 10.75. Okay, that's meters per second square. Then we have acceleration itself, which is equal to this is the magnitude. The two are perpendicular, so we can use Pythagoras theorem. Okay, so this should be equal to 10.75 squared plus 17.325 squared. Square root of that, we have a 20.39 meters per second squared. Right. So there we go. We found the velocity as well as the acceleration, their magnitudes of the ball when t is equal to 1.5 seconds. So I hope this video was helpful, and if it was, give me your thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and I'll see you in my next screencast.